Let us start this lecture with a quotation. Entropy is a non-conserved property based on Clausius inequality. Unlike the widely used term energy, the entropy provides a measure of disorderedness of matter that with time increases. To lead a decent and effective life by organizing our work in proper line, one can follow the path of least entropy by consuming in our life least energy. So, this is what we have learned from the second law of thermodynamics, and what we will do now, we will just recapitulate certain thing what we have learned and about entropy. We have seen that process can take place in certain direction and which will be satisfying the increase of entropy principle, that is Sg greater than equal to 0. Of course, for reversible process it will be equal to 0, and if it is violating the principle of entropy increase, then it will not really take place. So, as I told that a process will be taking place in a particular direction, not that all the direction whatever one can have, and that stipulates the what you call direction of the process, and in other words the feasibility of the process, right. And as I told earlier that the entropy is a non-conserved property, unlike the energy. Energy is a conserved property, and we know that according to the increase in entropy principle, that it will be goes on increasing, and there is no question of such that the conservation of entropy principle will be there like the energy. Of course, whenever the process is reversible, I mean which is the ideal case, then entropy can be conserved, right. Otherwise, it will be goes on increasing for all real processes. And we can also judge the performance of the engineering system, right, and how good or how bad it is, and what are the identify also the what you call irreversibility, right. And once we identify the irreversibility, then we will try to reduce it such that entropy generation can be minimized. And entropy generation is basically a measure of magnitude of the irreversibility in a what you call process, right, or in a system, and it is basically establishes the criteria for the performance of engineering devices. As you go along, we will see that we will try to find out various criteria how to judge about the irreversible extent of irreversibility kind of things. We will do that, but before that, let us now dwell into some applications of this entropy what we have learned in the last lecture. So, one way is that we can talk about basically a process diagram, like let us say we are having a PV diagram, we can convert it into TS diagram and so on and so forth. It will be helpful for to visualizing the process. So, we know that ds is basically dq by t for a reversible process, right. So, from this I can write down like what will be dq. dq is basically dq is equal to t and ds. Of course, this is meant for the reversible process, right. Then we can write down this one, and if it is for a cyclic process, right, then we can integrate it over here and this thing, right. And if it is cyclic, right, we can say that for that can be integrated over, let us say if it is station 1, I can integrate from station 1 to station 2, and this strip is nothing but your TdS is, which is equal to dq, and this is of course meant for the internally reversible process, right. That means basically system will be reversible, surrounding may not. So, that that area, the total area can give me how much heat, because this is temperature versus entropy. If I integrate, I will get how much heat interaction is taking place during this irreversible process. This area will give me, and that indicates the integration, right. And according to the first law of thermodynamics, for a control mass system, and considering that there is no kinetic energy change and there is no potential energy change, we know that du is equal to dq minus dw, right, that we know. So, and for a reversible process, the work done is nothing but your PdV and dq is TdS. And if I substitute these values here, if I substitute these values dw here, in place of dw PdV and in place of dq TdS. So, what we will get? We will basically get an expression that is du is equal to TdS minus PdV. So, if you look at the first law of thermodynamics now combined with the second law of thermodynamics, right, because through that heat dq we have already considered. Of course, this is valid for a reversible process, right. Now, if I integrate this thing for a cycle, right, what will happen? What will happen? For a cycle, I mean a whole cycle I am integrating. So, we have seen from the first law of thermodynamics, cycle process, the internal energy will be 0, yes or no. So, for the cycle, whole cycle, this term will be 0, because it is going from state 1 to 2 and then coming back again reversibly. So, therefore, a change in internal energy will be 0, is a property. So, therefore, it will be 0, right. If that is the case, then we will get TdS integral is equal to the PdV. That means, and we know that PdV is a work done. So, that you can very well get from this here. That means, this process TdS, if you look at that, will give me in a cycle the work done. The work done is basically this portion. That means, this hatch portion what I have given, this is nothing but your TdS, right, and integral. And if you look at, it is taking QH amount of heat from the source and it is rejecting QL amount. So, this process is basically this portion is the what you call the work done. And for isentropic process, and as I told that net work done is basically the area 1, 2, 3, 4 in the TS diagram, that will give me the work done. And for an isentropic process, we know that dq is equal to Td. Isentropic process means adiabatic and reversible. So, therefore, what it would be? That will be 0, right. That means, that ds, what you call ds will be equal to 0, because temperature cannot be 0, right. So, therefore, that means if I take the isentropic process between the what you call state 2 and 3, right, that will be isentropic expansion, right, in a Carnot cycle. So, that will be what? S2 equal to S3, entropy is remaining constant, in this case is equal to SB, right. Similarly, for compression process from state 4 to the 1, that is S4 is equal to S1 is equal to SA, right. And we can now express this Carnot efficiency in terms of entropy diagram. From this we can do, for example, that is basically we know that Carnot efficiency QH minus QL divided by QH. And what is QH? QH is nothing but TH, this is your what you call temperature TH, right. This is TH and this is your TL, right. So, SB minus SA, right, this is SB, right, and SA, and the QL is nothing but TL into SB minus SA and divided by the TH SB minus SA. So, that what will happen, this will cancel it out. So, you will get the efficiency Carnot efficiency is equal to 1 minus TL by TH. We have already done that, it is just to relook at it in in terms of entropy, which is much easier than if you remember that we had done for the ideal gas, right, considering, and then we have arrived at similar expression. But this is a very simpler way of doing expressing Carnot efficiency in terms of the sink temperature and the source temperature. So, this is the one aspect how you can apply the concept of entropy for constructing the not only the process diagram, but also the understanding the process and deriving the expression for the Carnot efficiency and other things as well. So, let us look at the TdS diagram relationship. So, that we have already know that for the control mass, the first law of thermodynamics is basically dq minus du is equal to dw. And we have also derived this expression TdS is equal to du plus Pdv, and per unit if you look at mass wise, so that will be TdS, this is a specific entropy is equal to du plus Pdv, and that unit if you look at it is kilojoule per kg, and this unit will be kilojoule basically, right. And this expression is known as the first Gibbs equation, right. It is known as the first Gibbs equation, and this is what you call we can also derive another Gibbs equation by considering the enthalpy. Enthalpy is nothing but U plus PV, and then if you differentiate that, you will get dH is equal to du plus Pv plus Vdp, right. And what is this du plus Pdv? This portion, this is nothing but your, according to the first Gibbs equation, that is nothing but your TdS. So, this portion is TdS, right, TdS. So, therefore, I can express this equation in terms of the what you call that TdS is nothing but equal to dH minus Vdp, right. So, this one is known as the second Gibbs equation, which will be very useful for finding out entropy change. And keep in mind that this we have derived considering the control mass system. However, it will be both valid for the closed system and also an open system. This expression will be valid. So, and this will be process will be valid for the both reversible and irreversible process. Okay. Although we have assumed the what you call reversible process in deriving this, but it can be valid. And if you look at like I can divide this equation what you call second Gibbs equation by the T, and I will get this T, and then I will get this expression, that is T ds is equal to dH by T minus Vdp by T. And similarly, if I will divide this expression first Gibbs equation, I will get ds is equal to du T plus Pdv by T, right. So, for an ideal gas I can write down here, that is nothing but Cv dt by T plus this, if I take ideal gas law, what will be, that is R by V into dV. If I will integrate it, so what I will get? I will get is equal to C V ln T 2 by T 1 plus R ln V 2 by V 1, right, is not it? We have already done for an ideal gas. This is valid for ideal gas, right. And otherwise also you can integrate, provided you know the C V is a function of temperature, like of course, that is for ideal gas and some other things, and in this case we have assumed that C V is constant, it is not a function of temperature. Therefore, we have taken out and integrated. Similarly, you can also derive an expression for here like d s is equal to C p ln T 2 by T 1, right, for an ideal gas, that is ln P 2 by P 1. Okay. So, that one can derive and then get an expression. So, therefore, from this one can really apply this relationship very easily and find it out. So, now we will take another example how we will calculate basically mixing of non-identical gases. What we will take? We will take ideal gas of course, n moles of gas at pressure P and T is kept in one chamber, and there is another chamber and which contains NB amounts of NB moles of gas at same pressure, and then we will remove this partition, right. If you remove this partition, what will happen? The gas will be mixed, right, yes or no, and when it will mixed, then there will be change in entropy, and that is irreversible process. Now, how to calculate that? Entropy change for an irreversible process, because mixing is an irreversible process. You cannot really reverse it back. So, one can actually substitute this process in terms of reversible process, right. One can think of that as if this gas A is coming through something reversible isothermal expansion process, and then of course, after that what is happening, that it will come to the pressure P A, that is a partial pressure, and then it will be passing through a semi permeable membrane, again that is also reversible by forcing the gas. Similarly, you can think of there is a in the similar way that gas B basically having like reversible isothermal expansion here, and then it will be again forcing through a semi permeable membrane kind of things to that. So, that both will be mixed and with this chamber, right, which is at a partial pressure A and B, and total pressure will be P. So, that is basically imaginary, but of course, in reality one can do like, but not for all the gases. For oxygen there is a foil through which you can selectively pass the gases. So, but however, this process we are considering an imaginary reversible process. So, that means the mixing of which is irreversible process consists of two reversible process. One is isothermal expansion, of course, isothermal reversible expansion, and other is forcing of gas reversibly, right. That is the thing what we are considering. So, now for the gas A, if you consider this is gas A, right, the isothermal expansion process, for that we will have to find out entropy change for the gas A, that is dq by T, and you can express dH minus V dP, that is we have already done that, is divided by T, and in this case it is an isothermal process. So, this will be 0. So, then it is equal to minus V dP by T, and then what you call, you can express this for an ideal gas equation in terms of what you call V by T is equal to R by P, right, and then you will put this, of course, N will be there, the number of moles, right, and then I will find out NR dP by P, and you can integrate this and then find it out what is the expression. So, that will be change in entropy is equal to minus Na Ru ln P P A by P, because it is going to the partial pressure of A, like from the pressure P. And for the forcing of gas through the semi permeable membrane, right. So, that is entropy is change in entropy is 0, that is the second process, right, that is equal to 0. Similar expression we will be getting for the gas B, right. We will get delta S B is equal to minus N B R U d P by P, right. And of course, when you integrate this thing, you will get delta S 1 B basically N B R U ln P V by P, and del S 2 for the gas B will be also equal to 0. So, of course, we know that partial pressure is basically equal to the mole fraction, this is mole fraction, which is Na by N, N is the total mixture, in this case N is equal to Na plus Nb. So, we can express that in terms of P A as X A P, X A is the mole fraction, and similarly P V is equal to mole fraction of B into the pressure. So, if I will add this this thing delta S for both the gas A and B for the path 1, then it will reach minus N A R U ln X A minus N B R U ln X B. So, we know that for delta S 2 for the second process forcing the gas reversibly through the semi permeable membrane, that is equal to 0. So, therefore, the total entropy change during this mixing of the gas will be equal to N A R U ln X A minus N B R U ln X B. And of course, per unit mole you can express in the similar manner, right, that is equal to minus R U X A ln X A plus X B ln X B, of course, in the bracket that one. So, mixture for a, of course, we have taken two gases, right, that might be nth gases, like nth number of gases one can think of. So, the total entropy change, one can say the change in entropy, that is what you call small s, right, and is equal to R U X I ln X, sum over the number of gases, whatever it will be. It may be 2 gases, it may be 5 gases, it may be 10 gases. So, you can find out basically entropy change for what you call mixture of gases during the mixings, right, and which is an irreversible process. We have basically found out reversible way and do that. So, if you look at that way, that X I is less than 1. So, therefore, entropy is always positive quantities, because X I is less than 1. So, it also says that it adheres to the principle of entropy increase, right. So, we have discussed a lot about entropy, but a question might be lurking in your mind, what is the physical meaning of entropy, right, because we are talking about it, we are using it, we know how to calculate during a process, and it will also tell us about the quality of energy, and it will talk about the feasibility of process, lot of applications we are having, right. What is the physical meaning of that? So, entropy can be viewed as a measure of molecular disorder or the randomness, because the molecule will be moving around, right. And if you consider this definition, you can see that for a solid, let us say, what will be the entropy? For the gaseous, what will be entropy? In which case the entropy will be higher. The very simple definition itself will tell you that the solid case, the molecules are in a very close contact and they vibrate around their own positions, they will not really change the position. Therefore, the entropy will be what you call very, very small, and of course, the liquid is basically a little movable. It goes together, but it moves, and therefore, the liquid entropy is higher and gaseous entropy is the highest among all three phases, all three states of matter. And if you look at, I had given earlier an example, like earlier days our bond in the family was very strong, therefore, we are having less entropy. That means, stress level in life was very, very small, because all stress being taken care by others, shared by others. And later on, we are a family degenerated in our country, and then we became liquid state, entropy increases, and today we are in gaseous state, right. So, therefore, we are facing lot of what you call problem in our life, right, because we are moving at a faster rate, and therefore, the efficiency is coming down and then entropy is increasing. So, if you look at from the statistical point of view, we can express the entropy, and that is the Boltzmann relationship, that is equal to S is equal to K ln W. K is your Boltzmann constant and W is the thermodynamic probability. That will be representing how randomness and the extent of randomness available in that. So, if you look at, if you consider the matter, and of course, this will be dependent on the temperature at which, if you take a solid, if it is as a higher temperature, the entropy will be, higher you can consider. And if you take a pure crystal, right, and you will find that entropy will be 0 only when the temperature is 0. If the temperature is different, then it cannot be 0, it will be some finite value. So, that basically says the third law of thermodynamics, we state that a pure crystalline substance at absolute 0 temperature is in perfect order, and therefore, its entropy will be 0 or is 0, right. So, that is nothing but your third law of thermodynamics. Just to illustrate how, what you call entropy of a physical meaning. Let us say there is a what you call, let us consider a load, something is there in the cart and it is being pulled by few people on left hand side, let us say, and pulled by the right hand side. Will it really move or it will vibrate, move here and there. So, then if you look at the basically it will be in the random order, and the similar situation in our case also, like if you consider you might have gone to our Kalyanpur crossing, that everybody wants to go, but as a result nobody could manage to go in a traffic jam and it resulting into a traffic jam. So, there might be several examples I can give you, like that where you we encounter the entropy. I will give another example. Suppose before examination you are trying to read, study a lot, and then when you will go to the exam hall, then it will be a blackout. Suppose you can't do something, then you cannot retrieve back the your what you call the information from your memory, because it is not being orderly placed. And I will give another example, like suppose for example, like in your room you have kept the books, right, or you are in a library, if the books are kept randomly, it is very difficult to locate the book. That means, in that case the entropy of that library, in the rooms, the library, it will be very higher order. So, higher the order of the entropy, it is very difficult to handle, So, therefore, one has to be this thing, and disorganized energy basically does not create much useful effect, although we may be using it. So, therefore, one has to take entropy into our like what you call consideration and minimize the entropy by organizing ourselves, right. So, that is the thing. That is why if you look at when I look at you people and compare when I was in your place, that we are used to work less. You people are all the time busy, right, and working hard. Let me tell you harder than what I could think, but if you look at the net effect is not that effective and you are not on an average scale, not all, right, people in the what you call more effective. So, therefore, to be effective in this thing, one has to organize oneself, and that is the says that you will have to minimize the entropy in life. So, till now what we have done, so till now we have basically looked at how to handle the control mass system or the closed system. But however, we need to also handle the flow system, where flow mass will be entering and leaving and there will be some interaction kind of things, and then how to handle that. We will do in a basically similar way, that is let us consider a flow system here, and in this case some mass is entering in this case, and if I say this is my I inlet and this is my exit, right, and there is some shaft work, right, there is some shaft work is going on, and there is some heat interaction also. Let us say some heat is entering here and this thing, and then and as a result there will be some entropy change also, like the entropy will be change, right, sorry, entropy change will be there, generation will be there. Now, this is I call it as basically this dashed line, I call it as a CV, control volume, right. But we have not derived anything till now, the expression for the entropy change, which we have seen delta S is equal to dq by T plus Sg, right, entropy generation, that we have seen. Now, that is applied only for the control mass system, but we have this is a problem where the flow is entering and it is leaving out, right, mass is entering and leaving out, right. If I say this is mass in and this is mass out, right, exit, then how we will do that? We will do in a similar manner the way we handle first law of thermodynamics. That means, we will say that this process, flow process will be can be converted into series of non-flow process, right. We have done like video camera, you convert into various snaps, still images, So, therefore, we can do that. We will consider that at time is equal to T, let us say a certain amount of mass is entering, this is my system. Now, what is the system? The red color what I have shown here, and this is my system, right, at time t. And at the time dt, the system becomes, this is a new system which is having the certain mass is about to leave this control volume. And in the at time t, the certain amount of mass which is shown in this A region, that is about to enter into the control volume. Is that clear? Then what we will do? We will take this one as a system on the left hand side what I have shown, and the right hand side what I have shown is a system between the time dt, and dt is very small. So, therefore, we will apply this delta S which we have derived for the control mass is equal to the delta S equal to dq by T plus Sg. S is the entropy generation. So, let us do that, and at the time t, the entropy of the system what it would be? It will be the entropy whatever is there in this system in this portion, right, and the entropy is entering. If you look at this is basically entering into this is m dot I S I into dt, that is entering, and then total entropy which is at time t, and then this amount of entropy is entering during time dt. And similarly, at time t plus dt, the entropy change of the system will be basically m t plus dt into mass at t plus dt and entropy at t plus dt time, right, is equal to the amount of what you call entropy is going out in this, that is m dot E S E into dt, right. So, and this balance we will have to do by using the what we call entropy change for a control mass system, because we have considered a time t is one control mass system and time t plus dt is another control system, right. So, we have already know this expression, and what we will do, we will put that thing like in that is nothing but your change in entropy here at the exit minus the entropy at the inlet, right. Because this is at the entropy at the time t plus dt, and this is entropy at the time t, right, and you just change in entropy is equal to q dot into dt divided by t, right, and that is nothing but your entropy generation rate, right, during time dt, and then and q dot is the heat transfer rate during time dt. Therefore, q dot into dt by t, it will come over here, that is nothing but your dq by t, and this Sg is nothing but entropy generation rate during time dt into dt, right. So, you will divide this what you call by time, right. I can divide by this time t here and t here, this will cancel it out, and then when dt is tending towards 0. So, we will get basically an expression like this, and that is nothing but your ds by dt plus m dot I Sc minus m I Si, right, is equal to q dot divided by t plus Sg, right. This is the expression for what we call entropy balance in the case of your control volume system or the flow system. So, if you look at that, we can rewrite, I mean like I will take this q dot t in that whatever the entropy is entering, like inlet, and then I can write down m dot E Sc, I like in this here plus S dot J. And for a steady flow process, right, what will be happening, that entropy change is equal to 0, right, entropy change will be equal to 0. And of course, the mass is conserved according to, because steady state process there is no accumulation of mass. Therefore, m dot I is equal to m dot E is equal to m dot, right. And once equation becomes basically the equation 1 which we derived just now is equal to m dot into Sc minus Si, that is the change in entropy between the exit and the inlet, is equal to the heat transfer rate divided by T and plus Sg. That means, what it says change in entropy is basically will be greater than equal to q dot T, right. Okay. And similar expression we have got also for the control mass system, but only thing is that here it is the mass flow rate, that is the thing, and this is the also heat transfer rate that is coming. That means, entropy rate which is considered here. And for adiabatic process, what it would be? Q will be 0, right. So, therefore, the change in entropy will be always greater than equal to 0, right, for an adiabatic process. And for isentropic process, that is equal to 0, right. Isentropic process, that is nothing but your m into Sc minus Si equal to 0 for reversible process, reversible and adiabatic, that is nothing but isentropic. So, Se is equal to Si, that is entropy will be remaining same at the exit and the inlet for an isentropic process. And if you look at what are the applications of the second law of thermodynamics? That is, I have already discussed that thing. Let us summarize, that is to identify direction of a process. That means whether the process is feasible or not, that it will say, and to determine the degradation of energy during the process. That means, what are the irreversibility, because in irreversibility energy will be degraded. One example is the friction, like mixing. There are another example where energy will be lost, you cannot really retrieve it, right. And assessing the quality of energy, what will be the, like suppose I am having large amount of bed, but its quality is low, so that I cannot really use it properly. And determine the maximum possible performance of an engineering device, because that will give us limit, like with which we should strive for. And predicting the degree of completion of chemical reaction and phase transformation, that we will be using basically, of course, we will not be discussing, but we want to calculate the equilibrium product in a chemical reactions, right, which we can determine by applying the second law of thermodynamics or the entropy, right. And let me tell you, we had a discussion about the adiabatic temperature, right. We have taken a very simple, approach by which we felt that okay, we know the product, but actually in the real situation you will not be knowing the product. You will have to calculate the equilibrium, what we call it, products, and by assuming the temperature, and then you will have to calculate the adiabatic temperature, and it will go on. It is quite a complex process of determining the adiabatic temperature, which we had done in a very simple manner. That is not the actual case one has to do. So, therefore, is very important to look at that. So, these are the applications what one can think of. So, what I am thinking, let us take an example like that an engineer claims to design an air flow device which takes 3 kg of air at 200 kilopascals and 380 Kelvin and delivers 1.2 kg per second of hot air stream at 100 kilopascal and 500 Kelvin, and it also produces 1.8 kg of cold air stream at 100 kilopascal and 300 Kelvin, right. And this device does not require any additional energy as a heat for its operation, or also there is no work being also produced or given to this kind of device, right. But is his claim is feasible or not, that is the thing we need to check. So, question arises how to go about. It might be coming to your mind, is it really possible such a device? If you look at, this is the one what we are having, right. If I look at, this is the station 1 and 3 kg per second of air is entering, right. And what is the pressure? Pressure is something 200 kilopascal and temperature is something 380 Kelvin. And one stream is coming out as basically mass is 1.2 kg per second and pressure is 100 kPa and temperature is 500 kPa Kelvin, right. Temperature is 500 Kelvin, 380 to 500, and it is giving also another mass is 1.8 kg per second of air. Of course, this is air which is entering, right, air, and pressure is again 100 kPa and temperature is something 300 kPa. So, this if you look at, this is the hot stream and this is your cold stream, right. So, how to go about it? How to go about it? How will I approach? Basically, it is a simple one. What you will have to approach? You will have to do the three things. This is a what you call flow system. So, you can consider a control volume as the boundary of this system, that is your control volume, and you will have to do a first is you will have to assume what are the assumptions here. What are the assumptions? That is a steady flow process, these are assumptions, right. Steady flow and a change in kinetic energy, right, is equal to 0 and change in potential energy is equal to 0, right. So, for that if you want to really find out, I mean like what you will have to do? You will have to basically look at mass conservation and then energy conservation, then you will have to do a entropy balance, right. Second law of thermodynamics, that you will have to do. So, if you look at mass balance, right, what is that? M dot 1 is equal to M dot 2 plus M dot 3, is not it? Is it balance? It is balance because M dot 1 how much? It is 3 kg per second, as that then the hot stream is 1.2 kg per second plus and the cold stream is 1.8 kg per second, therefore, it is balance. So, then it is satisfied, the conservation of mass is satisfied. So, therefore, that is possible, till now we are possible. Then what you will have to do? You will have to find out the first law of what you call thermodynamics for a control volume, that is energy balance, right. So, what it would be then? M dot 1 H 1 is equal to M dot 2 H 2 plus M dot 3 S 3, yes or no, right. So, we know from this mass balance, that is M dot 1 is equal to M dot 2 plus M dot 3. So, I can write down that is M dot 2 plus M dot 3 H 1 is equal to M 2 S 2 plus M dot 3 S 3, right. Okay. So, we will have to check this equation like, or I can write down also this way, that is M dot 2 H 1 minus S 2 plus M dot 3 H 1 minus S 3 is equal to 0. If I satisfy this equation, that means it will be true, and we are also, we can assume another thing, this one ideal gas equation, we can assume ideal gas equation, right. So, if you look at what I will do, I can find out, that is basically mass, what is the mass here? Mass is M dot 2 1.2 and I can assume constant Cp, right, and Cp of air what it would be at this temperature, and like ambient temperature you can consider, that is into 1.005 kilojoule per kg Kelvin into temperature, what is T1? T1 is 380 minus S2, what is S2? This is your 2 stream and this is your 3 stream, right. The S2 is 500 Kelvin plus M dot 3, what is M dot 3? Is 1.8 into 1.005 and T1 is your 380 minus 300, that is 3. Is it 0 or not? Actually it is 0, right. If you calculate, that is equal to 0, right. In the similar way, by applying the second law of thermodynamics, I can write down that is m dot 1 S 1 is equal to m dot 2 S 2 plus m dot 3 S 3, then what else? This is adiabatic process, there will be the q dot t will not be there, right, and there will be also S g, right. Yes or no? It will be, that is that we do not know, right. So, how I will find out, I mean what we will do, we will have to do in the similar way. In place of m dot 1 I can write out m 2 plus m dot 3 into S 1 is equal to m dot 2 S 2 plus m dot 3 S 3 plus h dot g, right. What we will do, we will basically can write down as m dot 2 S 1 minus S 2 plus m dot 3 S 1 minus S 3 is equal to S dot g, right. Okay. Now, can I evaluate this S 1 S 2 or not? I can write down S 1 minus S 2 will be basically C p ln T 2 by T 1 minus R ln P 2 by P 1, yes or no, right. So, similar way we can find out that. So, if I know T 2, T 1, I know P 2 by P 1, these are known. So, I can find out that happens to be, we can find out that will be something, and if you put this mass also, right, m dot 2, right, and together you will find out 0.57, right. And I can find out S 1 minus S 3 is equal to minus 0.07 kilojoule per Kelvin. So, if you look at this term becomes like is equal to m dot 2 S 1 minus S 2 plus m dot 3 S 1 minus S 3 is equal to, you will find out 0.5, I will just add that kilojoule per Kelvin, which is greater than 0, right. You will find out this some finite value. So, if it is greater than 0, then we know that it will be basically what to call, that means S g is finite, right. If it is greater than 0, that means the process is possible, right, and that is nothing but your what to call S dot g, right, which is greater than 0. So, therefore, process is possible, right, process is feasible. So, by this way you can find out, right, how whether the claim is right or wrong. We have seen that S dot g, if it is greater than 0, then the process is feasible. However, if it is equal to 0, then the process is reversible. But in case this S dot g is less than 0, then the process is not possible at all, it is not feasible. So, we have learnt here how to apply basically second law of thermodynamics for a flow process or a control volume system, you can say. Thank you very much.